Okay, so your textbook presents solubility rules in this fashion. It says, okay, the top here is a list of everything that is usually soluble. So nitrates are usually soluble, acetate is usually soluble. That means that no matter what I put with NO3 minus, it's going to dissolve in water. No matter what I put with acetate, it's going to dissolve with water. Chloride is normally soluble, but if I happen to connect it to any of these three, so silver, mercury, and lead, then they precipitate. So these exceptions mean that they're solids up here. Okay, so if I take Ag and Cl, it would form a solid. It would precipitate. Similarly, if I took bromine and silver, or bromine and mercury, like that, all of those will precipitate. Sulfates are usually insoluble except when they're paired with strontium, barium, and mercury and lead. Okay, we saw that when we were doing last week's experiment where we made barium sulfate. It was the white powder that made the light go out because the ions were removed from the solution when we formed it. So we knew that barium sulfate doesn't dissolve in water. We knew that that would form a solid because we saw it last week. There's a few things that almost always form solids. So sulfide, if I make something connected to sulfide, it will normally be a solid. Insoluble means solid over here. Except if we pair sulfide with ammonium, that makes it aqueous, or calcium or strontium or barium. Okay, so those are the exceptions. So that means the ones for the bottom half of this chart, these are ones that would be aqueous. Carbonates are normally solid, except when they're with alkali metal cations. That means group 1. Group 1. So if I put lithium carbonate, that would be Li2, it would be aqueous because it's an exception here. It's an alkali metal, it's in group 1. And so if I pair that with carbonate, it would not precipitate. But if I pair calcium with carbonate, it does form a solid, okay, because that's not on our exceptions list. So that's how we use this chart. Another way to present the same exact information is in a chart like this, where the things that are soluble are in red, and the things that are insoluble are in green. So what we notice is that basically all of group 1 is always soluble. There are no exceptions over here. There's nothing we can pair group 1 elements with to make them solid. Similarly, ammonium, always soluble. It doesn't matter what you match it with. It's always going to stay aqueous. Nitrates and acetates work the same way. Chlorine, bromine, and iodine are usually soluble, so they're usually dissolved, except for when I pair them with any one of these three items over here. Okay, now down here at the bottom, carbonates are usually a solid, phosphates, hydroxides, and sulfides. Usually all solids, except when paired with anything in group 1, because we said at the top group 1 is always soluble, and ammonia right here. So basically we're saying these things are usually insoluble, except when they're paired with things that are always going to dissolve. Okay, so that you can use a chart like this to help you write reactions. So like, for example, if I'm doing a problem that says, you know, maybe that silver nitrate reacts with I don't know, let's say, so silver is Ag, nitrate is on the back of the periodic table, it's NO3. Since it has NO3 in it, we said there's no exceptions, NO3 is always dissolved, we're going to say that's aqueous. And so then it would be something like silver nitrate reacts with hydrochloric acid, which is an acid, so it has to be aqueous, to form silver chloride and I don't know, nitric acid, let's just say. Anytime the word acid is in there, it's automatically aqueous. And then Ag with Cl, Cl is normally aqueous, but when you pair it with Ag, it forms an insoluble solid. So that this kind of information is really good to learn because it helps us to figure out what state of matter things are in when I do a reaction. Okay, so we said that you can have solutions that are made out of a combination of a liquid and a gas. One of the examples was soda. You have basically a water solution with some sugar and other things, but water's the solvent, and you put in some CO2. And it dissolves right in the water, and that's what makes the soda taste tart and makes the pH very low. So we could take other gases and we could mix them with water if we wanted to. Different gases mix with water to different degrees. Here, this graph here is showing us that the red line, helium, has the lowest solubility. It's the lowest down on the curve here of all of these choices. So that means that it dissolves in water, but not as well as like oxygen does. Okay, so now the next question is, if we increase the pressure, what happens to the concentration of gas in the solution? So if I increase pressure of gas, what we're seeing, so like if I start with, say, very low pressure here, and then I increase it, well, our solubility increased. So as pressure increases, the solubility of a gas also increases. And that makes sense, because if you're increasing pressure of a gas, you have literally more gas molecules being pushed against the liquid. So they sort of seep into the liquid easier. To think about temperature effects, we want to look at gases and solids separately. Okay. Oh, by the way, the pressure changing, say if we increase pressure, the solubility of a solid is not affected because solids are not compressible. I could squish it all day long and it's not going to make any more solid dissolve. Okay, so here we're going to look at temperature effects, and so that means like as temperature increases, so going down this way, what happens to the solubility of a substance? So if we're looking at methane here, if we have low temperature, like maybe 5 degrees Celsius, we have somewhere around 2.2 millimolar, milli like milliliter. And if we increase it to just 40 degrees, a little bit warmer than room temperature, just slightly warmer than the human body, if we increased it to 40 degrees, the solubility is more like 1.1, so it's almost half. So what we're seeing is, as the temperature goes up, the solubility of a gas goes down. The reason for that comes to the fact that if this is our liquid here, and if we're at a cool temperature, we have just a few particles of the solvent that are kind of in gas phase. So that means that I could fit in more gas particles that are not, that are not solvent. I could put more, say, methane in there. So this is what happens, when it's low temperature. If we heat up this flask, okay, so high temperature. If we heat up this flask, what's going to happen is you're adding more energy to the solvent, so you get many more solvent particles in the gas phase, and it's like very, very crowded right over the liquid. So when I try to put in a solute, it's kind of hard for the particles to get in there. They're sort of fighting a crowd of solvent molecules that are in the gas phase. So this is the reason behind our trend here. What we're seeing is that there's more solvent molecules in the gas phase when it's hot, and they block the way. Okay. Now, solids are a little different. When we increase the temperature for a solid, generally speaking, so we increase temperature going from the left to the right. Generally speaking, things become more soluble. So let's look at this yellow line, the lead nitrate here. At roughly 0 degrees, we could fit about 38 grams into 100 grams of water. If we increase it to, say, like 50 degrees Celsius, it's, about 85 grams. So that's an increase. So as we increase the temperature, the solubility of a solid increases. This is generally true, but not always. This Ce2 compound down here is doing something funky. But generally speaking, as we increase temperature, the solubility of the solid increases. The reason for that is that we're increasing kinetic energy. And when kinetic energy is higher, that means the atoms are moving faster, so they're running into each other more frequently. So you can imagine like a room full of kindergartners on sugar, The sugar is heat, and so the more sugar you give them, the faster they're running around, the more likely they are to collide with each other, which is bad for kindergartners. But for molecules that you're trying to dissolve, that's good, because you only dissolve things when they run into each other. If the particles aren't moving, then they're not gonna mix. Okay, and then the reason for this was on the last slide where I drew the little picture of the beakers for you. They're less soluble because there's more solvent particles in the gas phase, and the solute can't get in. Okay. The bottom line here is, in all cases, like dissolves like. We can make things dissolve to a greater or lesser degree by changing temperature and mixing and all these things. But fundamentally, if I have something that is nonpolar, it's not going to mix with something that is polar. Those two things are literally oil and water. Okay, so it's possible to start out with a solution, but keep adding so much solute that I can't get any more to dissolve. When that happens, it's called a saturated solution. A saturated solution always has solid in the bottom of the beaker. So this is my salt water. We had 36 grams of NaCl in 100 grams of water, which is the same thing as 100 milliliters, basically. Okay, and then that was a saturated solution. It would be clear. It would look like water. You would have no solid in it. But if I keep going and I add more salt, then it's all going to collect at the bottom. So here in this example, we put in 60 grams of NaCl. Only 36 of that can dissolve, so I can figure out how much is hanging out on the bottom by just, subtracting. So down here we have 24 grams of NaCl just hanging out. The individual particles don't stay solid or dissolved. They kind of switch back and forth. We call this an equilibrium. It means that the individual particles can one of them will dissolve and a different particle will form the solid. So these processes are kind of going continuously. That only happens if you have a saturated solution. Unsaturated solutions are the ones that have 36 grams of sodium chloride or less. Okay, so I can use these graphs here to help us figure out when things become saturated. All right, so if we look at the graph on the right, say I have, let's see, which one do we want to use? Let's use potassium nitrate, the green one here. If I have potassium nitrate at 20 degrees, it's capable of dissolving about 30 grams into 100 grams of water. So if I put 30 grams or less, anywhere along this amount, it will be unsaturated. If I put 31 grams, then it will be saturated, and I'll have 1 gram of that substance hanging out on the bottom of the beaker down here. Okay. So I want you to watch this video. It is a video where they have a flask filled with a substance where they've heated it up and dissolved as much as they could in the hot solution, and then they let it cool down really slowly and they don't bump it. And so you'll see a couple seconds into the video that the liquid ripples. That's because they bumped the container. And when that happens, something really neat occurs. Okay, so go ahead and watch that. And this is called a supersaturated solution. This is only achievable if you cool things down really carefully. So you get something saturated when it's hot, you cool it down really carefully, and you don't bump it. You can do the same thing with water. Go on the internet, go on YouTube and look. You can make supersaturated ice sculptures with water if you're very careful.